Hello. So this is the short tutorial on the near field using Python. So first of all, thanks goes to Asif Bhai for this. He's the one who showed me. He's the one who showed me how the correct or updated methodology for the near fields, and also the one who gave me the idea and also the code for generating the plots in Python as well. So this would not be possible without him. Okay. So first of all, before we used to manually do the hard labor of disabling the nanoparticles, running the simulation, extracting the data, and then enabling it, repeating the whole process again. Very tedious. So the script just does the whole thing all on its own. So you disable the sphere here, run the simulation, and then you get the electric field data from the monitor that we placed in the XY plane. This get electric function was used, and from the numerical documentation page, you see that the get electric function returns this, which is the squared magnitude of the electric field. And this is a scaled up version of the energy density. Just trust me on this. Just trust me, bro. And the near field is nothing special. This is just a term used to describe uh, how we near field is essentially nothing but the electric field density over a region of space. Okay. And it's called the near field because we're observing it at the nanoscale level. Like we're very close to the source. That's why it's near. We're near the source. That's really it. Nothing fancy to it. It's just the electric field. So this yields the squared magnitude of the electric field density, which is analogous to, which is proportional to, not analogous, which is proportional to the energy density. And if you want an analogy, just refer to circuit theory, and you know that the squared magnitude of the potential field or the voltage gives us the power or the energy density as well. So this was done here, and then we ran the simulation again, but this time we enabled the nanoparticle cluster here, and then we ran the simulation, collected the near field, the monitor data, and then all the variables that are saved in the script workspace were saved as a MATLAB file using MATLAB save. And wherever our I'm losing my mind, the FTTT simulation file is, the MATLAB file will be saved in that same directory. I'm really losing my mind. Whoa. Okay. So inside this MATLAB file, we have our electric field data over the 2 dimensions. And we're gonna unpackage the data in Python, and then we're just gonna plot it. So this script does the same thing. Okay. First of all, what you would do is you would take the directory where this is stored. I usually like to just drag and drop, copy paste this here. This is the directory. Okay, just do what I did. If you're using Spider, that would be nice. Just get a way to find the directory and copy it here in this. Then once you're in this directory, you would have to copy the file name so that the code can open it. So you just paste this here. Okay. And then using the h5py package, we're reading the MATLAB file. And first of all, we get the field bare and the field data stored already, and the dimension data as well. Then this was converted, the field data was converted into a NumPy array, and this NumPy array using array.reshape was shaped to become 2 dimensions. So if you refer back to the numerical scripting workspace, you see that the dimension, this is a 4-dimensional vector. So that's why we used array.reshape to convert it back into 2 dimensions. And based on which plane you are simulating the near field or running the script for the near field, you would disable this and enable this if this was for the XZ monitor, which is not. So I'm just going to keep the XY enabled for now. Then we're doing the near field enhancement image, where we're comparing the bear with the field data with the nanoparticle. And then that was, we took the logarithm of that here. Nothing too fancy. And then we're just plotting it using IMShow, which is the standard for like plotting images. And the only thing to note here is that the CMap is jet to get the blue and red color scale, and this is the most important part here. So this is essentially whatever the data is, we're restricting the color to only 0 and 1, the 0 being deep blue, 1 being deep red, and these are just other plotting formalities. So if you just address these two and just run it, you'll get the plot, which is this. So you can change the title, whatnot, but this is it. And you can save this as a PDF file by just enabling this or just running it in the console. And in this workspace, you'll get the PDF. Whoa. I hope you got, okay, never mind. Okay, now I think, please, by money to the paper. Okay, hopefully, yeah, okay. Yeah, I know what I'm doing, guys. So, yeah. And we can use this PDF. The good thing about PDFs is that this won't pixelate. It's not pixelating. So it does not matter what mesh size you used. I used 5 nanometer mesh size because at first this is a PDF, this won't pixelate, and secondly we interpolated the data, meaning we smoothed out the data using Python somewhere here. Yeah, bilinear interpolation. Because of this, the data looks smooth. If I just disable it, it'll look pixelated. See, it looks pixelated, messy. Ugh. And with this interpolation code, it smooths out everything. Looks nice. And that's pretty much it. Thank you for following my YouTube channel. Please like and subscribe, guys.